Everyone on the internet seems to think they can build a Jetson One for the price of a used Honda Civic. It's just a giant drone. 8 motors, some batteries, and aluminum tubing. $5,000, tops. Okay. Today, we're going to test that claim. We'll start with nothing but an empty workshop and build a theoretical Jetson One-style aircraft, one component at a time. The frame, the motors, the propellers, the motor controllers, the batteries, the joystick, and finally, the flight computer that keeps the entire thing from flipping over. And after every major component, we'll update the running total. The challenge is simple. Can we stay under $5,000? Because at first glance, a Jetson One really does look surprisingly simple. There's no turbine, no helicopter transmission, no huge wing. Just 8 electric motors surrounding a seat. But once you start buying components capable of lifting an actual human being, the numbers change very quickly. So let's start with the cheapest part. First, we need something to hold everything together. The Jetson One uses a lightweight roll cage-style airframe. It looks simple, but that simplicity is intentional. The frame needs to be strong enough to support the pilot, batteries, and propulsion system, while remaining light enough for the motors to actually lift it. For a homemade version, one obvious option would be 6061T6 aluminum tubing. It is relatively light, strong, and widely used in lightweight structures. Based on the estimates we're using for this build, the raw aluminum tubing could cost around $700. That sounds pretty good. Our $5,000 dream is still alive. Running total, $700. But that is raw material only. We have not included TIG welding, jigs, machining, fasteners, labor, or any structural testing. And ideally, we would want the completed frame to weigh somewhere around 10 kilograms. Make it stronger by simply adding more metal, and the aircraft gets heavier. A heavier aircraft needs bigger motors. Bigger motors need more battery. And suddenly one cheap design decision becomes expensive everywhere else. But for now, we'll be generous. $700 for the frame. Next, we need to make it fly. This is where the $5,000 budget starts getting uncomfortable. A small brushless drone motor can cost $50. But that motor might carry a camera. We're trying to carry a human being. Suppose our finished aircraft has a maximum takeoff weight of around 200 kilograms. That includes the aircraft, batteries, and an 85-kilogram pilot. We don't want exactly 200 kilograms of thrust. That would leave virtually no margin for climbing or maneuvering. So let's target roughly 220 kilograms of total thrust. With 8 motors, each propulsion unit has to contribute a significant amount of lift. And now we're no longer shopping in the normal hobby section. Heavy lift electric motors can cost around $1,000 each at the lower end, and some can go far beyond that. Let's be extremely optimistic. 8 motors at just $1,000 each. That gives us $8,000. Running total, $8,700. And there goes the challenge. We haven't bought a single propeller. We don't have batteries. We don't have motor controllers. We don't even have a seat. And we're already almost twice our original $5,000 budget. But maybe we can save money somewhere else. Let's keep going. Those motors are useless without propellers. And again, these aren't the plastic props you put on a camera drone. At this scale, the propellers need to move a huge amount of air while remaining lightweight and stiff. Carbon fiber is one common solution. But large carbon fiber propellers are not cheap. Using the estimates for this build, they can range from roughly $500 to $1,500 each. Let's stay at the absolute bottom again. 8 propellers, $500 each. That's another $4,000. Running total, $12,700. We are now more than 2.5 times over budget, and the aircraft still cannot spin a single motor, because we haven't bought the electronics that control them. Each electric motor needs an electronic speed controller, or ESC. This component regulates the power going from the battery to the motor. And on a multicopter, ESCs do much more than simply turn motors on and off. There are no traditional ailerons or rudders controlling the aircraft. Instead, the flight computer constantly changes motor speeds. Increase thrust on one side, reduce it on the other. The aircraft rolls. Change another combination, and it pitches or yaws. This is happening continuously. And on a human-carrying multicopter, these controllers may need to handle extremely high electrical currents. According to the estimates we're using, high-power ESCs can cost roughly $200 to $1,000 each. Again, we'll take the cheapest number, 8 ESCs at $200. Another, $1,600. Running total, $14,300. Remember, we're choosing the low end of almost every price range, and we still don't have the single heaviest system on the aircraft, the battery. This is probably the biggest challenge in electric personal aviation. You need a battery with enough energy to keep the aircraft flying, but every kilogram of battery must also be lifted by the aircraft. Add more battery, you gain energy. But you also gain weight. More weight requires more power. More power drains the battery faster. That is the trap. A Jetson ONE-style multicopter may consume tens of kilowatts during flight. Takeoff and climbing can demand even more. For our theoretical aircraft, let's assume a battery system, somewhere around 12 to 14 kilowatt hours. Using the source estimates for a one-off high-performance pack, the battery could cost around $3,600 to $4,200. We'll use $3,600. Running total, $17,900. $17,900. And let's look at what we actually have. A pile of aluminum, 8 motors, 8 propellers, 8 motor controllers, and a battery. There is still no pilot control system, no flight computer, no safety system, no wiring harness, no displays, no landing gear, and definitely no engineering. Our $5,000 Jetson has already become an $18,000 pile of parts. And this is where the hidden costs begin. Jetson One does not require the pilot to manually control 8 individual motors. That would be almost impossible. Instead, the pilot uses a simple joystick. You command the aircraft to climb, turn, or move forward. Then the computer figures out what every motor needs to do. A proper aviation-style control stick can itself cost around $1,000. Could you use something cheaper? Absolutely. You could install a gaming joystick if you really wanted to. But remember what it is connected to. If the joystick in your gaming computer fails, your character crashes. If the joystick in this machine fails, you crash. Let's add the aviation-grade control. Running total, $18,900. And now we reach what might be the most misleadingly cheap component of the entire aircraft. The hardware inside a flight controller can be surprisingly inexpensive, maybe a few $100s. There are advanced hobby flight controllers available for far less than a single motor. So let's say $500. Running total, $19,400. $20,000. And now we're done, right? Not even close. Because the flight controller hardware is only the body. The software is the brain. The aircraft needs to know its attitude, altitude, position, motor speed, battery condition, pilot input, and ideally, whether any part of that information is wrong. If a gust pushes the aircraft sideways, the computer must correct it. If the pilot commands a turn, the computer has to calculate how 8 motors should respond. If one motor begins producing less thrust, the system needs to recognize the change before the pilot even understands what is happening. All of this occurs many times every second. And if the control algorithm is badly tuned, something much worse can happen. The aircraft can become unstable, oscillate, roll unexpectedly, or in the worst case, flip. You can buy flight controller hardware for hundreds of dollars. You cannot buy years of engineering and flight testing for hundreds of dollars. And this is where the real cost of the aircraft starts becoming almost impossible to calculate from a shopping list. Let's say one motor fails. What happens? On a camera drone, maybe you lose the drone. That's unfortunate. But nobody is sitting in the middle of it. On a manned aircraft, losing one motor cannot automatically mean losing the vehicle. That means the propulsion system needs additional capacity. The electrical architecture may need redundancy. Sensors may need backups. The control system needs failure logic. The software needs to understand what happened. And most importantly, all of it has to be tested. You don't simply tell customers, "Don't worry, the computer should handle it." You need repeated flight tests, motor out tests, high load tests, temperature tests, battery tests, emergency procedures. And every test costs money. Aircraft get damaged. Parts get replaced. Engineers get paid. Software gets rewritten. Then you test again. None of those costs are sitting visibly inside the finished aircraft. But somebody still has to pay for them. Now imagine the worst-case scenario. Multiple systems fail. The aircraft can no longer maintain controlled flight. What is your final backup? A whole aircraft ballistic parachute is one possible answer. But once again, buying a parachute is only the beginning. Where do you mount it? What happens when it fires? Can the frame handle the opening shock? Will the parachute clear the propellers? How much altitude does it need? How does the pilot activate it? And most importantly, has anyone actually tested it? A parachute that works perfectly in a computer simulation means very little if nobody has ever fired it from the real aircraft. Testing means prototypes, deployments, destroyed components, redesigns, more deployments, more money. And notice something important. We still haven't added any of that to our running total. Our $19,400 estimate is still basically just hardware. This is the biggest problem with the "I can build it for $5,000" argument. People count the visible parts: motors, aluminum, batteries, propellers. But they don't count the invisible parts: engineering, software development, startable failed prototype aircraft, failed components, structural testing, flight testing, tooling, manufacturing labor, quality control, documentation, training, customer support, spare parts, warranty, facilities, and insurance. Imagine a company spends millions developing an aircraft and only builds a few hundred of them. Those development costs have to be spread across a relatively small number of machines. Car companies can spread engineering costs across hundreds of thousands or millions of vehicles. Personal eVTOL companies cannot. That is one reason low-volume aircraft can become extremely expensive, even when the raw materials don't look particularly exotic. Let's look at our extremely simplified bill. Raw aluminum, about $700. 8 low-end heavy-lift motors, about $8,000. 8 carbon fiber propellers, about $4,000. 8 low-end ESCs, about $1,600. Battery pack, about $3,600. Joystick, about $1,000. Flight controller hardware, About $500. Our theoretical total? Roughly $19,400. And that number is actually misleadingly low. Because we have ignored fabrication, welding, electrical wiring, sensors, displays, landing gear, seat, harnesses, cooling, connectors, emergency systems, structural testing, software development, engineering labor, prototype failures, flight testing, and manufacturing. So no, you are not building a real Jetson One equivalent for $5,000. At least not with the assumptions we've used here. Could you build something that looks like one? Probably. Could you build a machine that briefly lifts a person using cheaper hobby components? Possibly. But that is a very different product. One is a prototype man-lifting drone. The other is an aircraft you expect to fly repeatedly with a human on board. That is a different debate. This breakdown does not prove that every dollar of the Jetson One's retail price is justified. Retail price includes far more than the bill of materials. There is development cost, labor, facilities, support, overhead, and, of course, profit. So it is completely reasonable to believe personal eVTOLs should become cheaper. And they probably have to become cheaper if this technology is ever going to reach a mass market. But there's a huge difference between saying, this aircraft should cost less, and saying, I can build the same thing for $5,000. The second claim falls apart very quickly once you start buying real heavy-lift components. So, can you build a Jetson One for the price of a used Honda Civic? If all you want is a giant experimental drone that can lift a human for a demonstration, maybe you can get creative. But if you want a machine with reliable motors, high discharge batteries, redundant controls, stable flight software, emergency systems, and enough testing that you're willing to put your own life in it, $5,000 disappears almost immediately. Our extremely optimistic parts list reached nearly $20,000 before accounting for most of the expensive engineering. And that might be the biggest lesson here. The aluminum isn't what makes a personal aircraft expensive. The motors aren't even the whole story. The expensive part is turning a pile of drone components into something you would actually trust with your life. So here's the question. If someone offered you a Jetson One-style aircraft tomorrow for $5,000, would you actually fly it? Let me know in the comments. And if you want to see more breakdowns of personal eVTOLs, flying cars, and strange aircraft, subscribe. Thanks for watching.